As a physics teacher, I use lots of simulation and hands-on experiment to help my student understand physics topic such as electricity.
My name is Sam Sabo, and I took Regents Physics and I loved it.
Regents Physics.
Say it again.
I took Regents and I loved it.
I took Regents Physics and I loved it.
My name is Dion Ramcharan and I took physics and I love it.
I'm Christopher Laro. I took Regents Physics and I loved it.
My name is Steve. I took Regents Physics and I love it.
My name is Derek. I took Regents Physics and I loved it.
I took Regents Physics and I loved it.
My name is Louis. I took Regents Physics and I loved it.
My name is Abdullah and I took Regents Physics and I love it.
My name is Sula. I took Regents Physics and I loved it.
I took Regents Physics and I love it.
I took Regents Physics and I love it.
I took Regents Physics and I love it.
We took Regents Physics and we loved it.
As a part of AMS Research Action Project, recently I have developed a hypothesis: simulation is better than hands-on experiment. I have collected lots of data through a series of interviews. Let's take a look.
I support hands-on experiments more because to begin with, it's more, you can apply it to a lot more things.
I think I support the simulation better because although it's fixed and you don't really learn anything from it, but when you I think you just get the overall idea using the simulation, so you know what you're supposed to be finding.
I chose hands-on because I feel like I like touching and making sure I know what I'm doing first before I go on the computer and do the same thing.
And I'm Jared. I think hands-on is better because unlike simulations, hands-on actually will make you do more work, and like the experiments can be more exciting than looking at a screen, like seeing it in front of you rather than at the screen.
My name is Eric and I prefer hands-on experiments because I believe when you use simulations, they cause more of a isolation when you're trying to learn with physics. However, with hands-on, you can form groups and allow each other to combine all your known knowledge to solve a problem together.
After conducting a series of interviews, we seem to have reached a consensus that simulation is for understanding and hands-on experiment is collect the empirical data.
Simulations for data, hands-on experiments for the experience of clarification.
I like that. Simulation for understanding and hands-on experiment for data. Put it other way around. Simulation for understanding, I really like that. What about you? Simulation for understanding the natural phenomena. Once you have full understanding, then you do experiment to for what? For empirical
data.
For empirical data. However, we still wanted to reach out scientist Dr. Daniel Kavat for his opinion.
I think when you're starting out, some hands-on experience is good. I think especially with something like electricity that isn't so familiar to people in everyday life. Everybody has the experience of throwing a ball or pushing on something and watching it. But in everyday life, people don't have so much experience with electricity. So I think giving them some tangible hands-on experience is good. And then once they've developed some confidence and developed some understanding, then simulations can actually be clearer and easier to understand. Because real-life experiments are often complicated, don't quite work the way you expect, and it's hard to do an experiment perfectly. So once you have a little bit of experience and background, then a simulation can be a very effective.
Pass me one. Or you want to just attach it?
Yeah, sure.
Okay, so now this.
Where's the nails?
Oh my god, this goes here. Oh my god, and then this goes here. And now we take Another one, Handson?
I could try. I don't even know my shit.
This goes here.
Which one was just Snapchat?
It's not lighting up.
Why did
Maybe the other one.
You have to figure that out why it's not lighting up.
Maybe it's this way.
Hello, I'm Steven, and today I will be using the simulation to create a series circuit that will light up one bulb. First I got a couple of wires, and I'm using a rectangular shape. We will be using wires, and I'm going to make a rectangular shape because when making circuits, it's conventional to use a rectangular shape. And in the middle of these wires, we call this a junction. Middle of the two wires, we call this space the junction. Then we insert a battery inside the circuit, but then we get a short circuit. This is because there is no resistance inside of the circuit yet to suck up the power. So we have to add a bulb, and then this problem will be fixed. Connect it, and boom, it's lit. There's the current using this ammeter that measures the amps right here. We're going to split the junction, creating an opening so I'm able to place the ammeter in between. The reading that we have is 0.90 amps to measure the voltage. We have 8.9999. When I do the hands-on experiments, we have to use the real-life materials. For example, a bulb like this, a LED bulb, a wire like this, alligator clip, and a voltmeter and an ammeter, just like this, together in one. Since I was able to do the simulated series circuit successfully, I'm now confident that I will be able to do the hands-on lemon battery experiment. I'm going to teach you how to make a lemon battery. We'll be using 6 items. 1, a lemon, which has, this is the source of the electrolytes, the lemon acid inside of the lemon. 2, a nail, a galvanized nail. This has zinc, which we will need to make a anode. Copper wire. We will be using this as a cathode. We need the copper. LED bulb, alligator clips, and a voltmeter to measure the voltage of the setup. I'm going to make 2 terminals. One is the anode, using the zinc. Insert it to the lemon. And the second, the cathode, with the copper wire wrapped around so that there's a connection. It can't be this slim, but it has to be. Enough copper. These 2 are neutral. This has the atomic number 30, this one 29. We used these items because they're easily accessible. Are neutral. This has the atomic number 30, this one has the atomic number 29. 30 protons, 29. Connect it and it reacts with the electrolytes. The zinc likes to give up electrons, and the copper wire likes to receive electrons. But this can't happen unless you make a bridge using the alligator clips, like this. And to do that, this becomes a cation, which is positive, and this becomes a anion, which is negative. And now I'm going to use 5 lemons to make a series circuit and measure the voltage. The negative of this battery would connect to the positive of the second battery. Make sure that you do that. And then all you'd have to do is connect the negative with the voltmeter. Let's see what the reading says. It's 15. So with 2 lemons, you would have 15 divided by 10, which is 1.5 volts. Well, using the information and the direct relationship, we can infer that using 5, it would take approximately 3 volts. And now I'm going to attach all 5 and light up the LED. This LED requires 2 volts to power it, 2 volts. Positive. Negative. Positive. Negative. One more to go. Positive. Negative. Let me organize. Positive connected with the negative. Positive connected on this side with the negative of the 4th battery. Positive of the 4th battery is connected with the, with the negative of the 5th. Now using the last alligator clip, connect the positive of this one, the negative of the 1st, the 5th, positive of the 5th, negative of the 1st. The short side on the LED is the positive, and the long side is the negative. So, positive to positive. Try not to put like charges together because the like charges would repel positive and positive or negative and negative. You'd have to put it opposite because opposites attract. Okay. Short side, positive, positive of the 5th, connected to the long side, negative of the first. Now you can see that the LED light is lit. As you can see, the LED bulb is lit. This is because I use the chemistry to make the 5 batteries, and I use the physics to create a series circuit from the batteries to light up this LED bulb. The word to explain the chemistry of the lemon battery and for the so first we make 2 terminals. One zinc with the atomic number of 30. This means that it has 30 protons. And then second terminal copper with the atomic number 29. This means that it has 29%. The name of the terminal for zinc is anode. A-N-N-O-D-E. The name of the terminal for copper is cathode. C-A-T-H-O-D-E. And we could use many materials that have the atomic number 30 or 29, but we chose a nail, for a galvanized nail for zinc, and a penny for copper because these items are easily accessible. A little more chemistry. Both of these are neutral, meaning that they have the same number of protons and electrons. And this one over here is called a zinc atom. This one over here is called a copper atom. Now we need a source of electrolytes. We could use anything: potatoes, watermelon, yourself, you're a conductor. But we're going to use lemon acid because it's a great source for electrolytes, and that's what we need. Let me draw this draw this rectangle. Lemon acid. Electrolytes. When we connect these, symbolically connect it, then this the zinc begins to interact with the electrolytes, and it then becomes ready to give up electrons, because this is very sensitive to the zinc is very sensitive to the electrolytes, and it becomes ready to give up electrons. And for the copper, it becomes ready to receive the electrons. However, this can't happen because they aren't connected. We need a bridge to connect these two, zinc and copper. Today we're using the alligator clip because it has aluminum and it's easy to find. Nice. I'll draw a bridge. Oh, different color. And now it has a path to move to leave the zinc galvanized nail and head over to the copper penny. This is a bridge. Using the wire, when this happens and the electrons transfer, this becomes positively charged. Less electrons. This becomes negatively charged because it gains so many electrons. Now called a cation for being positive, and this is an anion for being negative. This statement and this statement are no longer true, so I'm going to go ahead and erase this. So the cation and the anion together make a potential difference between the two terminals. Another name for this in physics is voltage. Finally, my experiment shows that using the lemon battery, let me make a table. Lemons on one side, voltage on the other. It gave me 1.5 volt. Using 3, it gave me 2.6 volts. This has 29. Said 20. Mr. Ray, the numbers are getting confusing because they're so close. And
That's right. By using myself, because I'm also a source of electrolyte, as Steve explained. So I'm gonna put this side in my tongue and this side in my tongue, and that should light up the bulb. Let's see. However, we do not recommend you to do that at home unless it is less than 10 volt.
Alligator clips. Alligator clips. Yes. 1, 2, 3, 4.
So these are the alligator.
5. How much did we use? 5 or 6?
Doesn't matter.
I think we use 5.
Actually, you can just leave the nails in. Just leave the nails.
Yeah.
Then they'll forget.
It's just for us to clip, right?
Simulation for STEM education. Simulation for STEM education. Simulation for STEM education. Simulation for STEM education.
Sunlight takes 8 minutes just to reach your eyes. Inside, it's all atoms making open up our minds. But if you think that learning science isn't meant for you, or just not cool, there are formulas to prove it now. Better study up, I'll show you how. We're about to throw some science down. Evolution made your brain, heart, spinal cord, and also your eyes. Medicine made the vaccines, technologies that keep you alive.
Competition, impressed with how much you all know about physics and how much you've learned from rational. And congratulations to everybody, but I guess most of all, congratulations.
Describe all 5 models of atomic structure. Draw the model on the whiteboard. Why has the atomic theory changed over time?
3 minutes. Go.
Lewis.
Oh, wait, hold on.
Okay.
Ready? Everybody ready? Yes. Question number 1. Describe all 5 models of atomic structure. Draw the model on the whiteboard, and why has the atomic theory changed over time? You have 3 minutes.
30 minutes?
3. Well, you can use your phone. Full tones.
45 seconds.
Yep.
I'm just gonna put the initials. JJ something, JJ Thompson.
So the timekeeper will remind you how much time left.
60 seconds.
And Jazz is gonna carefully to make sure that they are fair.
Please, lend me your glasses. I wish I had more on the face. I lost them all. Lend me your glasses. Lend me your glasses. I can't see this. 30 seconds. And it changes sound like for each one.
I need your glasses too. Still can't see this shit. God damn it, that is
I'm betting that's like lines are the worst.
And
I'm just
9, 8, 7, 6, 5, 4, 3, 2, 1.
So we're gonna give 30 seconds to the judges to make a conversation and give their point.
Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh no, it's gonna keep it up. I don't know how to react to this. You want me to say it's a big laugh?
Congratulations to everybody. I was really impressed with all of the energy and the excitement and the good competition. impressed with how much you all know about physics and how much you've learned from Rashidul. And congratulations to everybody, but I guess most of all, congratulations to Sam, who
Yeah, Sam!
Yeah, she won the last time.
Congratulations to you.
And also can
Thank you, Mr. Bari, for being such a good teacher. Yo, guys, clap it for Mr. Bari.
Yeah, Mr. Bari! Yeah!
And Dr. Kabal.
Thank you.
All right, so.
All right, great.